All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be continuing learning about embedded Rust programming on the ESP32. Just give me a second while I set some things up. Okay, and hopefully today we are actually gonna, stick to what I what I plan on doing for the stream. Real quick, I know I literally just said that hopefully today we're gonna stick to what I plan on doing on stream. Real quick, I have been doing a little bit of research on how to use multiple modules with a single ESP32 because so the way that it works usually is, and I'm yet to do this in practice, but like I know the theory part of it, so I have like some idea. Um, Generally, when you're working with different types of modules, like let's say an LED or LCD module, a TFT display of some sort, or maybe an RF transceiver, or any similar kinds of modules that are for different types of functionality. Um, these modules usually communicate with the ESP32 over some kind of protocol, and the modules are usually set up like they are wired to do that kind of communication. It depends which protocol is being used. It's going to depend on the different. It's going to depend on the various modules. They don't all use the same protocol, but a lot of them do use common protocols. So it's not uncommon to see something like I2C or SPI or there's a couple others that I cannot remember the names of. Hold on, let me see if um wait, I wanna give you guys like a little list of okay, hold on. So microcontroller um serial communication. Actually, okay, there's serial and parallel communication, but I've mainly done research on serial communication. And within serial communication, you have synchronous and asynchronous communication. Synchronous usually involves some kind of clock line, so it's like the communication is done based on a clock signal. And in asynchronous, you don't need to have a clock signal. So the protocols that are developed to be asynchronous, they are built in such a way that they are able to figure out the communication without the need of a clock signal. Uh, I just wanna give you guys. There was a thing on Spark Fun. That was pretty decent information there actually. Give me a second. I'm just gonna open that up. Okay, so there's a very useful page here. Maybe I might open this up on stream itself. Yeah, I could open it up here. Give me a second. I'm just gonna switch, and then I'm gonna Google something. Man, today I actually became late to start up the stream because wait, give me a second. Spark Fun, serial communication. Yeah, I actually became late to start the stream because I spent some time cleaning up my room. Give me a second. Okay. Yeah, I spent some time cleaning up a certain section of my room, and I spent quite some time organizing a little bit of my electronics workbench, my electronics work desk, workspace, let's say. Oh, just a second. Have I switched from BRB? No, I haven't. Right, hold on. Okay. Yeah, this was the one. Why does the website look different here? And oh, in general, the website has kind of changed a little bit. So, if anyone is interested in learning about um, communication in let's say embedded electronics, I was about to say in microcontrollers, but I guess embedded electronics makes a little more sense because, like, if I'm saying in microcontrollers, then that kind of leaves out modules because the modules themselves are not really microcontrollers. So okay, we can read this, and we're not gonna like go too deep into this, but I just wanted to read this. Read well, not all of this necessarily, but a little bit of it because reading this, I did get to learn quite a bit about these different communication protocols. Here, it's not touching parallel. It's mainly sticking with serial, at least from what I remember. I think maybe it touches on something parallel related. Hold on, let's see what comes under this. There were also oh, this is like a whole list of tutorials. Never mind. Um, there was also a list of some of the specific protocols, specific types of communications. That's actually why I'd opened this up. Because I remember SPI and I2C and I2S also. I can't remember what the others were called. So give me a second here. So there's SPI, there's I2C, both of them are here. And then there's probably a couple others that are no, no, dude, there's okay, hold on. MCU serial communication protocols. So it mentions UART, I2C, SPI, which again, others being mentioned are USB, CAN, and that's not what I'm looking for. I guess these are the two main ones then, I2C and SPI. There are a couple others as well that do get used. One wire is one of them, where you quite literally only use one wire, um, and the entire protocol is designed to work with just that one wire. It's also interesting learning about, like, once you go into I2C and SPI, you learn that there are both software and hardware implementations, and each of them has their pros and cons. One major pro with using the software implementation of one of these protocols is that you can use it over any other pin. Like, let's say we are talking about one of the GPIO pins on the microcontroller. You could actually use one of those in order to do the specific communication that you're trying to do. Whereas if you are talking about hardware based implementation, you are limited to the specific hardware lines that they provide. So the specific pins that are for various, SPI peripherals, or for various I2C peripherals, you're limited to the specific pins that have been labeled for that purpose because that's the hardware implementation. But if you go with the software implementation, you can actually use many of the other pins on the microcontroller. And I might actually do that. See, when I was looking this up, because okay, my initial doubt, the question that I'd asked Gemini was that, so I know that a microcontroller can communicate with the module over some protocol that the module implements, and of course the microcontroller also implements. Um, like I2C or SPI or anything else, right? My question is, how do we go about communicating with multiple modules when you have a limited number of pins on the microcontroller? Like, how are you going about setting something like that up? Because you would need to switch from one to another in terms of like communication. And each of these, like, they have their own working mechanism. There's a bit of a setup required in each of them. You don't just like directly start communicating. So in that case, how are you going about switching between them? And uh, to be honest, I didn't really get a satisfactory answer at first, so I continued probing a little more. The answer that I got initially was because initially I'd only asked about SPI and I2C, and then I said, etc. I was hoping that Gemini would give me some extra information. Give me a second. Let me open up my stream on my I had a I had somebody's TikTok video um, playing before I'd locked my phone, and so when I unlocked it, then all of a sudden that video is playing. Uh, okay, cool. So the question that I had asked was, I said, okay, so I do projects with ESP32. I know that you can communicate with various types of external modules using various communication protocols like SPI, I2C, etc. Now, communicating with just one module is fine, but how do I go about doing things when there are multiple modules and I need to communicate with them using the same ESP32? How does that setup work? So Gemini suggested that for I2C, and this is because like each of these protocols, they have their own way of working. So the way that you go about using different devices, it kind of differs. Um, so for I2C, um, Gemini said I2C is designed for simplicity. It uses only two wires, SDA and SCL. How it works in I2C, every device has a unique 7-bit address. When the ESP32 wants to talk, it sends the address out on the wire. All modules hear the address, but only the one that matches responds. So the wiring is basically that all devices are connected in parallel to the same two pins. All the devices are connected in parallel to the same two pins. Okay, okay. Capacity up to 127 devices. The catch is that if you have two identical modules, like two OLED displays with the same hard-coded address, they will clash, and you will need a multiplexer or a module that allows you to change its address via a jumper. Okay, so this is one thing that I need to keep in mind. When I am using these different modules, I need to see if there's a way to actually change the address. Then, SPI. So SPI is much faster than I2C, but requires more wires. It uses MOSI, MISO, and so MOSI is master in, no, master out. MISO is master in, and then SCK, which is the clock. How it works, SPI SPI doesn't use addresses. Instead, it uses a dedicated wire for each device called CS or chip select or SS slave select. Wiring. The MOSI, MISO, and clock lines are shared by all devices. However, each device must have its own dedicated GPIO pin on the ESP32 connected to its CS pin. So I'm guessing this is where I could use the software implementation of SPI. I'm pretty sure ESP32 has both software and hardware implementation. Give me a second. ESP32 SPI. Let me go look that up. Because I remember seeing this a while back when I was doing research on MicroPython for ESP32. I was seeing all the various features that are available in the ESP32. And I remember seeing that there's both hardware based and software based implementations of certain things. So give me a second here. So there's SPI Flash API, there's SPI Master Driver, SPI Slave Driver. Um, This, I think this is pointing towards, okay, let's look at the hardware reference. No, I don't think the hardware reference is gonna give me anything. This is doing the API. This is showing me the API reference. Okay, peripherals API, provisioning API. I think it's peripherals. Okay, let's take a look at GPIO. Okay, so GPIO, GPIO 6 to 11 can be used for SPI. And then 16 and 17 can also be used for SPI. There's something called GPI. I need to look into what that is. Um, what else? What else? Where's I2C? Let me also look into I2C. Okay, I2C is a serial synchronous multi-device half duplex communication protocol that allows coexistence of so and so, so and so, so and so. Okay. No, this is not what I'm looking for, dude. Yeah, this is not what I'm looking for. The information that I'm looking for is on the Espressif website, but it, this is not what I'm looking for. ESP32 SPI software. Let's look at that. Um, software SPI. Okay, let's look at ESP32 MicroPython SPI. Okay, all right. Now, in here under reference for this, yeah, there it is. Software. Just a second. Okay, all right. Yeah, so there is software SPI bus, hardware SPI bus. I don't know why this is not shown on the Espressif site, or maybe I'm just being impatient with it. SPI master driver, SPI slave driver, SD SPI driver, SPI flash API. What is a flash API? The SPI flash component contains API functions relating to reading, writing, erasing, and so and so, so and so in the external flash. Oh, this is the flash API that's for which the communication is being done over SPI. The slave driver is a program that controls ESP32's general purpose SPI peripherals when it functions as a slave. Yeah, okay. So the documentation that I'm looking at here, actually let me open it up here so you guys can see it as well. I need to be careful of how many of these pages I open because it's gonna eventually start to slow things down. I'm getting a lot better information from the MicroPython version, which is kind of Interesting. ESP32, Micro Python SPI. Okay, then ESP32 SPI. Okay, that's it. Right. So here we have the MicroPython documentation for ESP32, or well, this is MicroPython in general. They have ESP32 specific um, documentation. And here, if you look on the left side, it mentions software SPI bus, hardware SPI bus, software I2C bus, and hardware I2C bus. And then there's I2S. This is actually where I'd seen the various communication protocols that were mentioned. I think one wire is also mentioned here. There, one wire driver. There were one or two other communication protocols as well. I can't remember what they were. But yeah, they have a bunch of these implemented for the ESP32 in MicroPython. Um, Hold on. Yeah. So with the software-based implementation, you are not limited to specific SPI related pins on the ESP32. You can use there's a wider range of pins that you can use. Um, Actually, I think any GPIO pin can be used at that point. I think so. I think that is the case. Though, okay, the good thing about the ESP32 is that pins often tend to be multi-purpose. So like one specific pin, it might be you might be able to use it as a GPIO pin, but then also capacitive touch pin, but then also some kind of SPI or I2C communication pin, or like maybe one or two other uses as well. It's of course going to depend on the specific ESP32 that you have. You can see the pinout of it, and you can find out what the uses are of each of the pins. I just remembered this that yeah, many of the pins that are GPIO pins, they also function as the other pins. Actually, okay, I I could open up. Hold on, ESP32 pinout. ESP32 Room 32 pinout because that's the specific one that I have. And fortunately, there seems to also be um, a pinout diagram for this on the ESP32 website. Um, Data sheet. I guess data sheet is what I'm looking for. Okay, give me a second here. Right, so I'm looking at the pin layout now, just waiting for the thing to load up. All right, here it is. So there's a bunch of use cases that I'm seeing in like each of the pins, and many of them are actually I/O pins. But I'm just going to read out some of them. So one of the pins, let's say IO34, it says GPIO34, but then ADC1, channel 6, RTC GPIO. That's like three different use cases in one. I'm trying to see if there's actually, it's not going to say SPI. I think it's going to say Mozzie or Miso or something like that. There's SD clock. Hold on. I'm just looking at this list. SPI clock as well. That's okay. Okay. Right. So I need to look into I need to look at the data sheet whenever I'm using a specific ESP32 to do any of this communication. Because okay, other than that, let's say I let's say let's say I wanted to use like an external module of some sort, right? I was trying to ask Gemini like if there's something that I could use. I can't remember what exactly Gemini had suggested that I use shift registers for. Hold on. Actually, the good thing here is that Gemini does maintain um, info of like older conversations, though I cannot remember if I had this conversation um, through Gemini's web interface or through the Gemini CLI. So give me a second here. Okay, a while back, um, you and I had a conversation that involved shift register. Oh, this was through Gemini CLI. I don't know actually if Gemini Web has um, is somehow connected to that and is able to like pull information from that that involved shift registers. Do you remember any of that? Can you tell me what it was about? It had to do with microcontrollers. Actually, did it have to do with microcontrollers? I don't remember. Okay, it says I found a conversation we had on May 18th. No, this is not the conversation that I'm talking about. However, let's keep reading it. Where we discussed various ways to control external components with a microcontroller like ESP32. While that specific discussion focused heavily on transistors and relays, shift registers came up in the context of expanding the number of output pins on your microcontroller. The problem that you mentioned was microcontrollers have a limited number of GPIO pins. If you want to control many LEDs, in my case, okay, this was an LED. Okay, and if you want to control many LEDs, a large display, or multiple motors, you can quickly run out of pins. The solution: shift registers. We talked about how shift registers allow you to control multiple output lines using usually eight or more, using only a few pins from your microcontroller, typically data, clock, and latch. The process: you shift data into the register bit by bit serially. Once the data is loaded, you latch it to the output pins all at once. This is often referred to as serial to parallel conversion. Why it's useful for your projects. We discussed. Okay, so this is an analog multiplexer. Okay. In the same period, we were also diving into hardware hacking and interfacing sensors like the ultrasonic sensor, and we discussed the importance of level shifters when your microcontroller and your components operate at different voltages. Actually, yeah, I might want to order level shifters as well. Let me write that down in my list of items to order, because I've definitely had situations where I might need to like step up the voltage or step down the voltage. Level shifter, um, 3.3V and 5V. Let's save that. Okay, all right. Where should I ask this next question that I was going to ask? I forgot what the next question was going to be. Well, okay. You know what? Let's not spend too much time on this. Let's what was I doing? So this is the Ratatouille window. Give me a second here. Right, this. So what I wanted to do was go through each of these examples and just implement it myself for my specific ESP32. Actually, I'm curious. I'm curious if they added any. I'm curious if they. What am I trying to say? I'm curious if they added in any options to allow us to run these examples on microcontrollers, on ESP32 microcontrollers, other than the one that the project was made for. Because in this case, the project was made for ESP32C3, I think. So let's take a look here. Okay, so we start with this. Okay, the entire material can be found at so and so. We can open that up again. Clone and change into the workshop repo. I've done that already. Okay, Windows users may have some problems with long path names. Follow these steps to substitute the path. Okay, repo contents book, which is a markdown sources of this book, and then intro code, which is code examples and exercises for the introduction course. All right. Okay, Hello World. The Hello World example is basically a project generated with ESP Generate. Templates are already covered in the Rust on ESP book. See generating projects from templates chapter for more details on how to generate a project from the ESP Generate and understand what. Okay, whatever. I'm paying attention to like the way the sentence is formed. I'm trying to make sense out of it, but whatever. Um, See generating so and so chapter for more details on how to generate. Oh, so you look at generating from generating projects from templates chapter in order to for details on how to generate a project from the ESP generate, and we look at understanding ESP generate for details on what's inside the template project. Actually, I don't think I've read this part. Though I let's open both of them. I think I have read this one, or maybe we never went too deep into it. I don't remember. Huh. Okay. Where was this supposed to be? We're gonna have to look for it ourselves. So we'll open the ESP Rust book or the Rust on ESP book. Here we have this using ESP generate and just ESP generate. Then application development, so and so, so and so, so and so. I don't think we need to look into this just yet. Though most of this information, I'll have to see how much of it applies to no STD. Okay, so ESP generate. ESP, I think we've looked into this already. So this is the installation of ESP generate. What's next after this? Yeah, okay, that's done. Then using ESP generate with all the necessary tools installed, you're ready to create your first Rust project running on an Espressif chip. And well, I believe I have read most of this. Actually, I do want to look into. So I haven't looked into the probe RS thing a whole lot. I'm not entirely sure if that's supported by. Um, I don't remember what exactly the issue was, but there was something that I had read that made me think that okay, perhaps I should leave this for later on. Let me open up ProbeRS. The ProbeRS project offers a suite of tools for interacting with embedded microcontrollers using various debug probes with robust support for Espressif chips. Besides flashing and monitoring, it provides robust debugging capabilities. If you're unsure whether you need it right now, you can skip the installation and come back to it later. Espressif chips, Espressif devices equipped with USB JTAG serial peripheral can use Probe RS without any external hardware. For devices lacking this peripheral, you'll need an external programmer like ESP-Prog. I think that's what caused me to set it aside. I think that's what caused me to set it aside. Let's take a look at ESP-Prog. I don't know what this is. ESP-Prog is one of Espressif's development and debugging tools with functions including automatic firmware downloading, serial communication, and JTAG online debugging. So, okay, I think what they're saying is that if we'll be able to use Probe RS if we have these chips, but if we don't have these chips, or more specifically this peripheral, if we don't have it on our chip, um, then we might need to use ESP-Prog. And I'm guessing, um, okay, hold on. I think I need to talk to Gemini about this. Just a second. Um, Actually, before that, I have a question about shift registers. Hey, so I had a convo with you a while back about shift registers. What I'm wondering is when it comes to shift registers, what's the what am I trying to ask here? What's the level of voltage and current, and how well does it handle analog signals, and would timing of various signals be affected if using shift registers? This is a horribly phrased question, a horribly formed question, but I'm hoping. Okay, so it's great to pick this back up. In our previous conversation, we touched on how shift registers like so and so are essential port expanders that turn a serial signal from your microcontroller, like an ESP32 or Arduino, into multiple parallel outputs. To answer your new questions about the technical behavior of these chips, voltage and current levels. Most common shift registers, like the 74HC, um, no, most common shift registers belong to the 74HC family. Voltage, they typically operate between 2 to 6 volts. If you're using an ESP32 or Raspberry Pi or an Arduino, these chips, these these chips handle those ranges perfectly. However, you must power the chip with the same voltage as your microcontroller's logic to ensure the high signals are recognized correctly. Okay, all right. That shouldn't be a problem because the ESP32 does provide like a separate 3.3 volt pin, so I can just like plug that in. Um, okay. Current. Shift registers are not power devices. Per pin, a single output pin can usually source or sink about 20 milliamps to 25 milliamps. This is enough for a standard LED, but not for a motor or high power relay. Total package. The entire chip usually has a limit, often around 70 milliamps. If you turn on all 8 pins at 20 milliamps each, you'll exceed the limit and likely fry the chip. This is why we often use shift registers to trigger transistors or Darlington arrays, like so and so for heavier loads. All right, handling analog signals. Standard shift registers are purely digital. They are only they only understand on or off. Can they handle analog? No. If you try to pass an analog signal, an analog voltage through a standard shift register, it'll simply interpret anything above a certain threshold as 1 and anything below as 0. The alternative, okay, there's analog multiplexers for that. Okay, good to know. Good to know. I don't need analog multiplexers right now though. Most of what I'm doing is digital, so I think I should be good on that front. Then timing and signal integrity. Since shift registers rely on a clock signal to move data, timing is a critical factor. Propagation delay. There's a tiny delay in nanoseconds between the clock pulse and the data appearing at the output. For most hobbyist projects, this is invisible. Then bit banging versus SPI. If you write the code manually, bit banging, the timing depends on how fast your code runs. If you use a hardware peripheral like SPI, the shift register can update at megahertz speeds. Synchronous output. One of the best features of so-and-so chip is the latch pin. You can shift all 8 bits of data while the outputs stay exactly as they were. Only when you pulse the latch pin do all the outputs update simultaneously. This prevents flickering or intermediate states from showing up on your LEDs or display while the data is moving. Okay, daisy chaining. You can connect multiple shift registers together. If if you can connect multiple shift registers together, the timing stays consistent, but it'll take longer to fill the entire chain. Example, 16 bits is twice as long to shift as 8 bits. Okay, that's done. Great. Now, next question here. I'm doing Rust programming for ESP32. In the docs, they mentioned probe RS, but they also mentioned that it requires a very specific peripheral called, what is it called? Called USB JTAG serial. They also mentioned that not all ESP32 chips have this. And I know for sure that I'm using one of the ones that they haven't listed as having USB JTAG serial peripheral. They mentioned that for other chips, I would need something called ESP prog. I looked into it and I'm kind of confused about what exactly both these programs are doing and why I'm not able to use probe RS on all ESP chips, and What else? What else? Oh, and what the limitation really is here. So I'm hoping that Gemini is going to just explain to me everything about what exactly these applications are doing, and then we can go into the limitations of the chip, or the reason why, um, using one of these applications with a quote unquote unsupported chip isn't possible. Okay, it can definitely be confusing because ESP32 is now a massive family of chips, each with slightly different hardware guts. Okay, to understand why you can't just plug any ESP32 into probe RS, we have to look at how the chip talks to your computer. The problem: how do we see inside the CPU? To debug a program, such as pause execution or reading memory, your computer needs to talk to the chip via a protocol called JTAG. Standard USB cables don't work. Standard USB cables don't speak JTAG. Oh, okay, hold up. To debug a program, your computer needs to talk to a chip via a protocol called JTAG. Standard USB cables don't speak JTAG, they speak USB. Therefore, you need a bridge or a translator between the computer's USB port and the chip's JTAG pins. Oh, so this becomes kind of like a USB to UART kind of situation, right? Because then the reason you need the UART thing is because the ESP32, at least the older chips, they don't understand USB, they understand UART. And so on the ESP32 itself, on the dev board, I mean, you have a USB to UART converter, which is what your USB messages kind of go through and get converted in. Um, Though I think the newer ones are probably, I think the newer ones do actually have that ability. I'm not sure. I'm going to have to look into what they've done to kind of make that possible, because there are some ESP32 chips. I forgot which specific one it was. There are some ESP32 dev boards where you have um, two USB ports. One of them they say is USB to JTAG, and no, one is a USB to UART, and one is just USB. So I need to look into that. I think I also need to look into USB on like a lower level in terms of like a protocol, because I do remember doing research on this a while back, and that's kind of why I know about this USB to UART thing. Um, because like the the issue there was that the computer speaks USB, right? And you have a USB port, but the ESP32 doesn't speak USB. At least, with the older ones, they don't speak. It doesn't speak USB. It can understand UART, so you would need a USB to UART converter of some sort, and the dev board usually has one on board, which is why you're just able to connect a USB cable into your ESP32 dev board, and you're able to have communication very easily. I think I need to revisit that whole thing again. Maybe I'll revisit it through this conversation. I should have asked this question on this computer instead of the other computer, so you guys would be able to see it. Or I should have asked it in. I can do that. Hold on, I can do that. Let me try this because I haven't been using Gemini CLI nearly as much ever since their whole like what do you call it, usage limits, the rate limits thing started causing issues for me. Ever since then I haven't been using it all that much. Which one do I want to show you guys? Oh yeah, I can probably do it here. Okay, back back. I do have a Gemini instance open here. This is going to take a couple of seconds to wake up. I think it's woken up now. Though this is Gemini Rust Learning. This is the wrong one. It's not what I'm supposed to be opening up. I also have this in the wrong thing. Give me a second here. Okay, so we have the traits thing here. I don't think I need this to be in Gemini Learning. Though, I mean, we are in this already. I can close this later on. So I'm just going to copy the entire prompt and drop it here. I just realized you guys can't see the thing, or well, I just remembered. Give me a second. Let me just drop the prompt in here. I should also change. Nah, it doesn't matter. Okay, hopefully I'm gonna get information here, and in the meantime, let me switch to. Oh, I also had an idea for something that I want to work on using Rust and Ratatouille. See, yesterday on stream, I was kind of scrambling to try and get DirDraw running, and that got me thinking, why don't I make my very own simple, you know, sketching kind of application? Just a simple application, a simple Rust-based Ratatouille application, because Ratatouille um, it provides you with a bunch of extra stuff that you would otherwise have to implement yourself. There's a bunch of systems and functions and stuff that have already been implemented, features, I should say, that have already been implemented, which would otherwise be my headache to implement. Um, if I was using something like Crossterm, for example, because Ratatouille is built on top of Crossterm. Crossterm is much more lower level, but like going lower level also means that you have to implement a bunch of things yourself. And I don't want to do that because why? Like, it's good for the sake of learning, but in this specific case, it's going to waste a lot of time because that's not the aim. What I'm aiming to do is just build a simple sketching application, a simple terminal sketching application, I should say. Give me a second. I'm still waiting on that response from. Okay, all right. So I need to close this, I believe. What do I have open? Oh shit, I have the Ratatouille thing open. I just realized that. I have the yesterday I was doing the Ratatouille thing. Why do I have that open here though? Yeah, why is it open here? I didn't I don't know. Whatever. Uh I need to detach from this, and then here I need to do temp Rust learning. All right, great. We are here. So let's see what the response was. Of course, let's break down the roles of probe RS and ESP prog. Hold on, there. Okay, at its core, this is about a difference between a debug probe and a debug runner. A debug probe is the hardware and the debug runner is the software. Okay, the goal, on-chip debugging. To, perf to perform low-level on-chip debugging, like setting breakpoints, stepping through code, inspecting memory, your computer needs to communicate with the processor's debug interface. The standard for this is a protocol called JTAG. The problem, bridging the gap. Your computer speaks USB, but the ESP32's processor speaks JTAG. You need a bridge to translate between them. This bridge is called a debug probe. The two scenarios. Scenario A, built-in debug probe, which is USB JTAG serial. Some newer ESP32 chips have a debug probe circuit built directly into the chip. This is the USB JTAG serial peripheral. When you plug a USB cable into these chips, you get not only the power. What? When you plug a USB cable into these chips, you get not only power, you get not only power and a serial console, but also a JTAG connection. No extra hardware is needed. Scenario B, external debug probe like ESP-PROG. Most other ESP32 chips, including the original ESP32, ESP32S2, etc., do not have this built-in probe. They expose the raw JTAG interface on a set of GPIO pins. Okay, to use these pins, you need an external debug probe that connects to your computer via USB and to the ESP32's JTAG pins. The ESP-PROG is Espressif's. This is a board? Hold on, I didn't realize that. This is a separate board. Just a second. Where have I opened this? Was it here? Yeah, it was here. Oh God. Okay. This is a separate board. Yeah, I can't do this. Yep, that is out of the question. How much does this cost? Let me see what the um cheaper version of this costs. Okay, ESP Prague, AliExpress. ESP Prague Development Board, JTAG, so and so, so and so. It's going for around $12. Give me a second, I'm just opening up this website. But yeah, I don't think I'm gonna be buying this. I need to see if there's another. Yeah, okay, okay. I probably don't need this right now. Right, the ESP Prog is Espressif's official low-cost hardware board designed for exactly this purpose. The role of Probe RS. Probe RS is a software component that runs on your computer. It's a powerful tool that knows how to drive many kinds of debug probes. In scenario A, you tell probe RS to connect directly to the ESP32's built-in USB JTAG serial peripheral. In scenario B, I didn't realize this. You still use probe RS even in scenario B. In scenario B, you tell probe RS to connect to your ESP prog board, and the ESP prog then translates the commands from probe RS into JTAG signals for the ESP32. Okay, that was very informative. Um, I would also like to understand the whole USB to UART thing. I know that that's a thing on ESP32 boards, especially the older ones. I don't really understand why it is used. So far, what I've gathered is that the PC speaks USB, and the ESP32 speaks UART, and that is why we need a USB to UART um, chip to translate the messages. But I feel like I don't really understand what this actually means. Hold on. I guess part of the reason is that I don't fully even understand the USB or UART protocols. Right. Let me hydrate while this answer is being generated, and then we can read. Okay. Excellent question. You've correctly identified the core function, but understanding why that translation is necessary and what it entails is key. Let's use an analogy. Okay. Imagine your ESP32 is a brilliant old school telegraph operator from the 1890s. Your PC is a modern high-tech logistics manager at a global shipping company. Oh God. Okay. UART, the telegraph operator. UART, Universal Asynchronous Receiver Transmitter, is like a simple telegraph system. It's the naive language of most naive native. It's a native language of most microcontrollers. How it works: it uses two wires, one for sending and one for receiving. It sends data as a series of electrical pulses representing ones and zeros. The asynchronous part is key. There's no separate clock wire to keep everything in sync. The operator on one end just starts uh, tapping out a message. The operator on the other end has to have already agreed on the speed, the baud rate, to have any hope of understanding it. If one is tapping too fast or too slow, the message is garbled. Okay. It's simple and direct. It's a very raw and low level way of communicating, perfect for two chips sitting right next to each other on a circuit board. This is your ESP32. It thinks in simple timed voltage pulses. It's great for talking to other chips on the same board, but it has no concept of the outside world. USB, the Global Logistics Manager. USB, Universal Serial Bus, is like a massive, managed international shipping network. It's the language of modern computers. How it works: It's a highly complex protocol managed by a host. The host is the host is a central manager that polls all connected devices, like your keyboard, mouse, webcam, etc. It's not just raw data. A device can't just start sending pulses. It has to identify itself to hold on. It has to identify itself to the host, saying, "Hi, I'm a keyboard." Wait for the host to ask it for data, and then package that data into complex error-checked packets with addresses, headers, and metadata. It's robust. It uses a pair of wires with differential sign. It uses a pair of wires with differential signaling, which cancels out electrical noise. This is why you can have long USB cables, but a raw uh, a raw UART signal would get corrupted after just a few inches. Okay, I didn't know that. This is your PC. It expects to manage a network of well-behaved devices, not listen for the faint, untimed clicks of a lone telegraph. Then the USB to UART chip, which is a translator. You cannot plug the telegraph line directly into the logistics network. The manager won't know what to do with the simple clicks. The operator would be overwhelmed by the complex shipping manifests. This is where the USB to UART chip, like so and so, comes in. It's it's the brilliant agent sitting in an office between the two, facing the PC. The chip presents itself as a standard generic USB communication device. Your PC's operating system sees it and creates a virtual COM port. Your computer thinks it's just talking to a classic serial port, hiding the complexity of the USB protocol from you. That's interesting. Your PC's operating system. Okay, the chip presents itself as a standard generic USB communications device. I need to know more about this thing. I guess today's stream is all about um, serial communication in embedded devices, studying serial communication in embedded devices. Okay, your PC's operating system sees it and creates a virtual COM port. Your computer thinks it's just talking to a classic serial port, hiding the complexity of the USB protocol from you. Facing the ESP32, the chip connects directly to the ESP32's UART, TX, and RX pins. It listens for the simple voltage pulses from the ESP32's telegraph. The translation in action. When the ESP32 sends a debug message, example serial.println hello, it's just toggling the voltage on its TX pin in a timed sequence of ones and zeros. The UART chip diligently listens to these pulses, gathers them into bytes, wraps them into a formal USB data packet, and sends it over the USB cable. Your PC's OS receives the USB packet, unwraps it, and delivers the raw hello data to the serial monitor. So the chip isn't just translating messages, it's fundamentally bridging two completely different communication paradigms, the simple point to point asynchronous world of UART and the complex host managed packetized network of USB. Older ESP32s didn't have the sophisticated and more expensive circuitry required for a native USB peripheral, so putting a cheap dedicated USB to UART chip on the development board was the most effective solution. Okay, that explains it. Now, my next question was here somewhere. Right. Okay. Am I able to copy this and then like, is that going to paste properly? Okay, let's try this. Because I'm not sure what's going to get pasted, give me a second. Okay. Right. Okay, so you mentioned um, something that I'm, hold on. There you go. I'm gonna, my God, can you type properly? Holy shit, there you go. Uh, my hands were like getting offset. So like I'm hitting I instead of O, I'm hitting B instead of N. I'm gonna need you, you're joking. I'm gonna need you to, okay, so you mentioned something that I'm gonna need you to explain in much more detail. You mentioned the following. Oh, oh God. All right. Wait. Yeah. Um, you mentioned something that I'm gonna need you to explain in much more detail because I don't understand how it or they work works. You said there. I'm not gonna bother formatting it. Right. So, what else were we supposed to be looking into? I mean, on the bright side, we are still learning something about, microcontrollers and their communication and stuff. Speaking of communication, I do need to look into communication communication uh, between communication over, not between, communication over various protocols. I kind of feel like I might need to use multiple microcontrollers to do this, unless I wanna, unless I wanna use one of my, well, okay, so what I was about to say is, unless I want to use one of my other modules that I have a bunch of modules for various purposes. I could very easily use one of those. But like if it's for specifically learning about something like SPI or I2C, I'm wondering if I should try to do the communication between two two ESP32s. Actually, I could ask this question to Gemini as well. For the sake of not running out of my limit, let me open up a new thing here. Um, I'm learning about ESP32 and Rust development on ESP32. I'm still pretty new to all this, I'm looking to learn about various COM protocols like SPI, I2C, etc. I'm wondering what a good way uh, to learn this would be. Should I try communicating between an ESP32 and a module of some sort, or between two ESP32s, or can I just practice the communication with one ESP32 alone? Okay, it's an exciting time to jump into ESP32 development, especially with Rust, the Rust ecosystem for ESP. Yeah, okay, that's fine. That's fine. Great. Awesome. To answer your main question, the best way to learn it is by communicating between an ESP32 and a dedicated peripheral module, such as a sensor, a display, etc. Here's a breakdown of why that is the best approach, along with pros and cons of the other methods. ESP2 peripheral module recommended. This is the gold standard for learning. You get to see how a standardized protocol like I2C or SPI is used to solve a real world problem, such as reading temperature or drawing on a screen. Why it's great: you have to read a data sheet. Learning to translate a data sheet's timing diagram or register. Well, that's not going to happen though, because I'm not going to be like I this is right. Okay, let me read what the thing is saying, and then I can, or what Gemini is saying, and then I'll tell you why I'm saying that that's not going to happen. Okay, why it's great. You have to read a data sheet. Learning to translate the data sheet's timing diagram or register map into Rust code is the most vital skill in embedded engineering. Okay, difficulty, medium. You'll deal with physical wiring and logic, but the other side, which is the sensor, is a fixed variable that follows rules. Suggested modules: I2, I2C, BME. Okay, that's the. You know what? I will be ordering these sensors for my. Um, I don't even know what to call it. Cyber gardening, cyber botanical experiments, let's say. For that stuff, I'm gonna be ordering a bunch of sensors. Actually, I also have a couple of ultrasonic sensors. I could try using those instead. I also have a couple of MPU 6050s, though that might be a tiny bit complicated to work with right now. I want to go for something that's like the simplest kind of sensor. I'll have to take a look at all the different sensors that I have, because the various modules that I have, they're for like a lot of very complex things. Like I have an I forgot exactly what it was, but it's an NRF RF transceiver. It's NRF something something. I forgot what exactly. But yeah, it's a RF transceiver. There's like a whole library for that, um, or rather a whole driver that implements all the functionality of that. I have two different types of TFT displays. For each of them, also, there's drivers that have been implemented. Though I am kind of tempted to implement something for these displays. If I'm able to, like, I'll have to take a look at the data sheet. And if I don't get overwhelmed by all the functionality of it, because I don't need to make all the higher level stuff, I just need to make the lower level stuff. Once I'm able to set that up, I should be good. Though there is another thing, right? I'm gonna need to. Well, no. Okay, okay. I just realized something. Yeah, I'm not gonna need to implement the math for drawing various shapes because that math already gets implemented using embedded graphics, the embedded graphics crate. I'm going to be implementing the various functions of that crate in order to make this this driver embedded graphics compatible. Just a second here. So the logic for drawing various shapes is already implemented. So the kinds of calls that need to be made, that's already been implemented. It's the final thing, like the actual communication with that peripheral, with that module, is what I need to be handling. So that would make it a little less daunting, I guess. So I'm going to have to mainly worry about the initial setup of that screen itself. Though the other thing is that I'm also very inexperienced with doing this kind of thing. And me implementing this kind of thing is going to take very precious time away from other stuff that I could be doing, that I need to be doing. So I don't know if I want to do that. Yeah, I don't know if I want to do that. I think maybe I could look into implementing something for one of the sensor modules, I guess. Once those sensors do arrive, I can look into the ultrasonic sensor. Maybe that's simple enough. I actually haven't looked at the data sheet for that. Hold on. Um, ultrasonic sensor. Okay, the specific one that I'm looking for is this one. It's either, okay, there's two of them that seem to have the, okay, I think it's HC. HCSR04. It's one of those cheap ultrasonic sensors. Um, I think I should be looking at, yeah, HCSR04 ultrasonic sensor data sheet. Okay, ultrasonic ranging module HCSR. Okay, fortunately, SparkFun has a thing online for it, so I can take a look at that. Okay, the working voltage is, okay, that's interesting. DC 5 volts. I need to keep that in mind. I forgot about that. I completely forgot about that. This is the thing. Working with, I think with Arduino, a bunch of things are like 5 volts, but like when you come to ESP32, it's 3.3 volts. It does provide a 5-volt thing, but the majority of the stuff is 3.3 volts. I don't remember if Arduino's like everything was 5 volts. I can't remember because like I played around with Arduino for some time because that was my very first microcontroller, Arduino Uno. And uh, after that, I kind of like moved on to ESP32. It could also be that Arduino Uno is like a 5-volt thing, but then future microcontrollers were, lower. I don't know. Let me see. So there's a timing diagram, and that's about it. You know what? I could probably, yeah, yep, I could probably do something with this. The data sheet is really small. Okay, so it says ultrasonic ranging module, HRC SR04 provides 2 centimeters to 400 centimeters non-contact measurement function. The ranging accuracy can reach to 3 millimeters. I don't know what ranging accuracy means here, but okay. The modules includes ultrasonic transmitters, receiver, and control circuit. The basic principle of work: using IO trigger for at least 10, I don't know if that's nanoseconds, for at least 10 nanosecond high level signal, the module automatically sends 840 kilohertz, sends 840 kilohertz and detect whether there's a pulse signal back. If the signal back uh, through high level, oh my God, through high level time of high output IO duration is the time from sending ultrasonic to returning. Okay. I didn't understand any of this. I'm gonna have to read it a couple of, oh, you know what I could do? Feed this into Gemini. Feed this into Gemini and at the words, at the very least, holy shit. At the very least, um, my stutter made me forget what I was gonna say. At the very least, the text, yes, that's what I was saying. At the very least, I can feed the text in, and Gemini could just like explain to me, because this is a very, very common sensor. Like this is very widely used. So like Gemini might just be able to explain all of it to me without even getting this text, but like I'm gonna give the text anyways. This module is not suggested to connect directly to electric. If connected to electric, the ground terminal should be connected to module first. Otherwise, it will affect the normal work of the module. What do you mean by connected to electric? Or yeah, I don't know. When tested objects, the range of area is not less than zero point 0.5 square meters, and the plane requests as smooth as possible. Otherwise, it will affect the results of measuring. Okay, all right. So this is one of the things that I can implement a driver for. This can be a nice testing kind of thing for me. I'm gonna have to take a look at all of the different modules that I have, because I have a couple of different modules for various purposes. I have one for I have an SD card reader, but I feel like that might be a little too complex for me to implement. I don't want to get overwhelmed with, though, okay, is this really the best way to go about it? Like implementing the thing myself? Let's look into the other options. So there was ESP32 to ESP32. Right. Communicating between two microcontrollers is excellent for learning asynchronous communication and custom protocol design, but it can be frustrating for a beginner. The challenge: if the communication fails, you won't know if the sender is configured wrong or if the receiver is bugged. You are debugging two sets of code simultaneously. When to do this? Once you understand how SPI slash I2C work conceptually, try to learn about master slash slave or controller slash target relationships. Then we have a single ESP32. You actually can practice with just one board using a loopback test. This involves connecting the transmit TX pin directly to the RX pin on the same board. Pros: zero cost, no external hardware needed. Cons: it's a bit sterile or sterile, whatever, sterile. It's a bit sterile. It conforms. Um, it conforms the hardware work. Confirms it. It confirms. I got so hung up on sterile versus sterile. I just forgot what I was reading. It confirms the hardware works, um, but it it doesn't teach you how to handle the quirks of different external chips. It's best for testing your initial Rust environment setup to ensure your UART or SPI drivers are initialized correctly. Man, some of the modules that I have are pretty sophisticated. Sophisticated. Um, so implementing driver, hold on, why am I messing up the spelling? Implementing the drivers um, for them just to study SPI and I2C seems a bit um, overwhelming. Let me change this a little bit. Some of the more simpler modules that I can think of are um, an HC SR04 sensor, and maybe actually I have a couple, but like I want to say the TFT display, but the thing is the TFT display has like a lot. Okay. But other than that, most of what I have is something like an NRF transceiver, a TFT display. What else? What else? There was a what do you call it? RFID. RFID RFID module. Um, oh, I have motor drivers and servo drivers. I have a couple of different types of modules that I'm just not able to think. I'm not able to think of like what all I've got. Oh, relay modules, and stuff like that. I might be buying a couple of gardening related sensors like temp sensors, humidity sensors, water level sensors, etc. Now let's see what the response is. Okay, I totally hear you. Jumping straight into wiring a driver for a TFT display or an NRF24L01, that's the one that I've got. Transceiver in Rust as your first project is like trying to learn to drive in a Formula One car. Those modules have complex initialization sequences that can be hundreds of lines of code. Since you're looking at gardening sensors, you're actually in luck. Those are the perfect Goldilocks modules for learning protocols, not too simple, not too complex. The gardening roadmap for protocols. Okay, water sensor. You won't use I2C or SPI here. Instead, you'll learn about ADC. Okay. Then for the temperature sensor, it uses one wire. One, it uses a one wire style protocol. If you get the other one, it uses I2C, okay. Soil moisture, that's capacitive, and that uses I2C. Why your current modules feel overwhelming? You mentioned so and so. Here's why they are tough for a beginner. SPI complexity. SPI requires you to manage the chip select pin manually or via a driver. Initialization. A TFT display requires a specific handshake, sending about 20 to 50 hex codes in a specific order just to turn the screen on. If you miss one, the screen stays black and you have no idea why. A cheat code for Rust, the embedded HAL. In the Arduino world, you just download a library. In Rust, we use crates. Instead of writing the driver from scratch, you can use a crate someone else wrote. This allows you to study the protocol without getting bogged down in the math. For example, you add the so and so crate to your project. You look at the source code. Because it's Rust, the code is usually very readable. You can see exactly how they use the I2C.write and I2C.read functions. My recommendation for your next step, don't start with the TFT or the NRF. Get an I2C sensor. Try to read the Who Am I register. Almost every I2C chip has a single byte at a specific address that just returns the chip's ID. Okay, did I also mention the... Okay, I did mention the HCSR something something, as in the ultrasonic thing. Okay, do I need to implement this myself, or is it sufficient to get a higher level understanding of the protocol and just use um, no, of the protocol just to understand how it's meant to be wired and how the code to use someone else's crate is meant to be written. This is, of course, keeping in mind that I'm not implementing my own driver for something, because, of course, in that case, I would need to uh, implement the SPI/I2C COM. Okay, this is a great fork in the road to reach. The answer depends on your goals. Do you want to be a driver developer or an embedded systems integrator? For 95% of developers, even professionals, understanding the protocol conceptually is sufficient. You don't need to manually toggle pins to understand I2C any more than you need to understand combustion chemistry to drive a car. Here's a breakdown of what sufficient understanding looks like versus implementing it yourself. What understanding the protocol actually looks like. If you are using someone else's Rust crate, like a driver for so-and-so sensor, you don't need to know the bit level timing. You just need to understand the hardware constraints, and the initialization logic. For I2C, you need to know addressing. Every device on the two wires has a unique 7-bit address. If two sensors have the same address, they will fight and your code will crash. Then pull up resistors. I2C requires resistors on the SDA/SCL lines to work. Many modules have these built in, but if you connect a bare chip, it won't work without them. Okay. Shared bus. If you, if you, no, shared bus, you can hook up, you can, oh my God, you can hook up 10 different I2C sensors to the same two pins on your ESP32. For SPI, you need to know the four wires. You have a clock, main in, main out, and chip select. Chip select, unlike I2C, SPI uses a dedicated wire for every device. If you have three SPI modules, you need three separate chip select pins on your ESP32 to tell them when to listen. SPI modes, there are four modes, combinations of clock polarity and phase. Okay. If the crate uses mode 0 and your sensor expects mode 3, you'll get gibberish data. All right. Why you should still try a bare implementation once. While you don't need to write a full driver, I highly recommend trying to read one signal byte from your sensor using just I2C.read, I2, using just the I2C.read function from the ESP without an external driver crate. Why? Because it teaches you how to read a data sheet. You look at the data sheet and see temperature is stored in so-and-so register. You write I2C.write address and so-and-so. Then I2C.read so-and-so. When the number pops up in your screen, the magic of how drivers work disappears, and you gain the confidence to debug someone else's crate if it ever breaks. The Rust way of using protocols. In Rust, the ecosystem uses a concept called dependency injection. It looks like this. The HAL you initialize, no, the HAL. You initialize the raw I2C pins using the ESP HAL. The driver, you give the I2C object to the driver crate, example, so-and-so display driver, and then you call display.drawPixel. You only need to understand the protocol well enough to do step 1, which is assigning the right pins and setting the speed. The driver handles the rest. Okay. Of all the modules I have right now, how would the HCSR04, is that what it was? I don't remember what the, yeah, HCSR04 module, or one of the um, DC motor driver or servo motor driver modules B. B for practice. This is a great selection of modules to pivot to. Interestingly, the HC so-and-so, DC motor driver, and so-and-so don't use I2C or SPI at all. Instead, they rely on timing and PWM. Oh, okay. Well, then I guess that changes things. While they won't teach you the bus protocols we discussed, they are arguably, they are arguably, holy shit, that is so hard to say. They are arguably better for a beginner in Rust because they force you to learn the most fundamental part about embedded programming, which is managing time. You learn how to use the delay peripherals in the ESP HAL. Then servo motors. Okay, all right. Servos can be controlled by a specific type of PWM signal. Okay, you know what? Hold on. No, I'm not gonna do it. I'm not gonna get sucked too deep into this. I'm gonna step away from this while I can before I get sucked too deep into it. There was a question that I'd asked uh, Gemini here, which was about the calm thing, and I got a nice long response. Okay, of course, the sentence is the absolute key to the whole concept, so let's unpack it in detail. It's a fascinating piece of software engineering that makes our lives better. We'll break it down piece by piece using our analogy of the telegraph operator and the logistics manager. The USB to UART chip is the bilingual translator that sits between them. Okay, the chip itself is as a standard generic. Okay, this this happens during a critical process called USB enumeration. Think of it as a formal introduction, or handshake that happens the instant you plug the device in. The hello. You plug in the USB cable, the PC's USB port provider, the, the, the PC's USB port provides power, and the USB to UART chip on the board powers on. The PC's USB hardware detects a new connection. The introduction, the descriptor, the PC or host asks the new device a fundamental question: who are you and what do you do? The business card. The USB to UART chip responds by sending a series of standardized data structures called descriptors. This is its electronic business card. Crucially, one of these descriptors is the class code. The USB standard defines many classes for common device types so that a single generic driver can operate them. You've used these all the time. Mass storage class, which is for USB flash drives. Human interface device class, which is for keyboards, mice, and gamepads. Audio class for USB microphones and headsets. Our USB to UART chip sends the class code for the communications device class. It's literally telling the PC my function is to be a generic communication channel. I'm not a mouse or a storage drive, I'm a data pipe. Your PC's operating system sees it and creates a virtual COM port. This is the PC's reaction to that business card. The OS reacts, the operating system, Windows, Mac OS, or Linux, receives the descriptors. It reads the communications device class code and says, aha, I know exactly what this is. I have a built-in driver for this job. Loading the driver. The OS loads its generic CDC driver. This driver's job is to be the manager for this specific device, creating the interface, the virtual port. This is the magic step. The driver creates a software only or virtual communication port that applications on your computer can see and talk to. On Windows, this appears as COM1, 3, 7, etc. in your device manager, and on Mac OS or Linux, this appears as a file in the dev directory, such as TTY USB or so and so. The COM port is a very old, very simple communication standard from the days of physical serial ports. By creating a virtual one, the OS is providing a familiar and simple interface for a modern complex piece of hardware. I'm going to need to explore this virtual COM ports thing and COM ports in general, actually, but I'm going to do that off stream. Okay, your computer thinks it's just talking to a classic serial port, hiding the complexity. This is a result of the abstraction. Imagine you're writing code in the Arduino IDE or platform IO. When you tell it to use COM3, your program does not need to know anything about USB. Okay, it doesn't know about descriptors, packets, or enumeration. All your program does is use simple commands like open, read, and write on the COM3 port. When you send data, your application gives the text to the OS passes it to the generic CDC driver, and the driver packages it into formal USB data packets and sends it to the USB to UART chip. The chip unpackages it and converts it into the simple electrical pulses, UART, that the ESP32 understands. When you receive data, the process happens in reverse. Okay, the entire complexity of the USB protocol is abstracted away by the combination of the USB to UART chip's firmware and the PC's operating system driver. Your computer, and more importantly, your software, gets to interact with a simple virtual version of a 40-year-old technology, the COM port, while all the modern high speed work happens invisibly under the hood. Okay, all right. Now, give me a second because it is time to. Hold on, where am I right now? Oh, okay. Just a second. For a second, I thought this is well, okay. Yeah, you guys can't see what I'm looking at. Never mind. Okay, I see someone here. Let me try and open up their stream. Okay, never mind. We cannot go there. Okay, I don't know what this person is doing. It does say first stream here, and their chat is verified accounts only, so never mind. Can't do that either. Uh, Hold on just a second. Okay, I think we'll go to this place. Uh, this person is doing. I hope they don't have any sort of thing that stops raids. Okay, so we're going to someone named Lana, XX Lana, and yeah, they are doing some drawing stuff. So we're gonna go hang out there. But yeah, that's gonna be it for today's stream. And I'm loving the fact that we've got more consistent streams now. Soon, I'm gonna start working on that tool for auto clipping, and yeah, dude. I need to get started on the LLM course just so we can learn about using the transformers library. But like in general, I kind of know how to use, because like the transformers library is pretty simple to get started with. If you pick any model that has transformer support, there's going to be a code snippet that shows you how to use that model through the transformers library, usually in either one or two ways. One is a simpler way, one is a more complex way that gives you a little more control. But yeah, it's really simple to get started with it. So if I wanted, I could get started like real soon. I think what I need to focus on is Optimum, because I need to convert the thing to Onyx. Okay. My time is running out, so that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time.